In this talk, I will present the idea of a Jarzynski equality for counterwork under reversed memory filtered driving. The main goal is to define a work-like quantity called counterwork, generated not by the original external protocol, but by an effective protocol obtained through a memory-filtered transformation of the original protocol velocity. Slide 2. One-sentence message. The central message is the following. A sign-inverting protocol memory kernel can transform an imposed driving protocol into an effective reversed protocol. Once this effective protocol is treated as the actual control parameter in a Hamiltonian family, the work generated by it is an ordinary Hamiltonian work. I call this quantity counterwork. The key result is that when the effective protocol reverses the endpoints of the original protocol, the free energy difference associated with counterwork is the opposite of the original one. Therefore, the exponential average of the counterwork is the reciprocal of the exponential average of the original work. Slide 3. Starting point, ordinary work. I begin with the standard setup. Consider a Hamiltonian system depending on a phase space point gamma and an externally controlled parameter lambda. The original protocol starts at lambda 0 and ends at lambda 0 plus delta lambda. The work performed on the system is the time integral of partial lambda h times lambda dot. With the usual Jarzynski convention, positive work is work done on the system by the external driving apparatus. If the system starts in the canonical equilibrium state at lambda 0, then Jarzynski's equality gives the exponential average of minus beta w as the exponential of minus beta times delta fw. Slide 4. Effective protocol by memory filtering. The next step is to introduce an effective protocol, capital lambda. Instead of using lambda directly, I define the velocity of lambda by applying a memory kernel k of t and t prime to the velocity of the original protocol. The important point is interpretational. This kernel is not a passive bath response function. It is a protocol memory kernel belonging to the external driving apparatus. Because of this, sign-changing kernels are allowed. In particular, a sign-inverting kernel can represent an active feedback or inversion mechanism. Slide 5. Counterwork. The counterwork C is defined as the ordinary Hamiltonian work generated by the effective protocol lambda. Explicitly, it is the integral of partial lambda h times lambda dot. Substituting the filtered velocity gives a non-local expression involving the kernel k and lambda dot. However, conceptually, the quantity is still ordinary Hamiltonian work. The non-locality is only in the construction of the effective protocol. Since the Hamiltonian family is h of gamma and lambda, Jarzynski's equality applies directly to C, provided the initial condition is chosen correctly. Slide 6. Free energy for counterwork. For the counterwork process, the initial state must be canonical with respect to the Hamiltonian at lambda of 0. Its free energy difference is f of lambda tau minus f of lambda 0. Therefore, Jarzynski's equality for C reads, the exponential average of minus beta C equals the exponential of minus beta delta fc. This is a standard Jarzynski relation. The only difference is that the process is driven by the effective protocol lambda rather than by the imposed protocol lambda. A crucial point is that the averages for W and C generally refer to different canonical preparations. Slide 7. Reversed endpoints. Now I impose the central condition. The effective protocol reverses the endpoints of the original protocol. Lambda of 0 is equal to lambda of tau, while lambda of tau is equal to lambda of 0. Then the free energy difference of the counterwork process is f of lambda 0 minus f of lambda 0 plus delta lambda. This is exactly minus delta fw. Consequently, the Jarzynski equality for C becomes the reciprocal of the Jarzynski equality for W. The product of the two exponential averages is equal to 1. This is the basic fluctuation relation result of the construction. Slide 8. Consecutive interpretation, equilibration step. If the forward and counterwork processes are viewed as consecutive stages of a single operation, there is an important preparation issue. After the original work protocol ends, the system is generally not in equilibrium at the final parameter value. Before starting the counterwork process, the system must be allowed to relax at fixed parameter. Because the parameter is fixed, this relaxation step contributes no work. However, It can exchange heat with the bath, and it prepares the canonical initial state required for the Jarzynski equality of the counterwork process. Slide 9. Jensen bound. The exact fluctuation relation concerns exponential averages. The product of the exponential averages for C and W is equal to 1, but this is not the same as the product of the exponentials of the average values. Applying Jensen's inequality separately to W and C gives that the exponential of minus beta average C times the exponential of minus beta average W is less than or equal to 1. Taking the logarithm then gives average C plus average W greater than or equal to 0. This is the mean level second law consequence of the fluctuation relation. Slide 10. Meaning of negative average counterwork. This bound clarifies the meaning of negative average counterwork. If the average of C is negative, then minus beta average C is positive, and the exponential factor involving C is larger than 1. For the product to remain bounded by 1, the exponential factor involving W must be sufficiently small. Equivalently, the average work, W, must be at least minus the average counterwork. Thus, average work extraction during the counterwork stage must be compensated by average work invested during the original operation. There is no violation of the second law. Slide 11. Kernel condition for endpoint reversal. We now ask, which kernels actually implement the endpoint reversal? The effective displacement delta lambda is obtained by integrating the filtered velocity. Changing the order of integration shows that delta lambda is the integral of lambda dot times the time integral of k over the output time t. To force delta lambda to be minus delta lambda for arbitrary protocol velocity, the integral of k over the output time must be minus 1 for every t prime. This is the sign reversing normalization condition. Slide 12. Simple example. The simplest example is a constant sign-inverting kernel, k equal to minus 1 over tau. For a linear original protocol, lambda of t equals lambda 0 plus t over tau times delta lambda. The effective velocity then becomes minus delta lambda over tau. If the effective protocol starts at lambda 0 plus delta lambda, it evolves linearly back to lambda 0. Hence, the effective protocol runs from the final value of the original protocol back to its initial value. This illustrates the reversal mechanism in the simplest possible case. Slide 13. Second law consistency. The sign-reversing kernel does not violate the second law. The reason is that the second law must be applied to the actual process generated by h of gamma and lambda of t. For the counterwork process, Jensen's inequality gives average C greater than or equal to delta Fc. If delta Fc is minus delta Fw, then average C is greater than or equal to minus delta Fw. Defining the dissipated work and dissipated counterwork, one obtains average W plus average C equals W dissipated plus C dissipated, which is non-negative. Equality occurs only if both processes are thermodynamically reversible. Slide 14. Zero coupling limit. A useful consistency check is the zero coupling limit. If the Hamiltonian does not depend on the controlled parameter, then partial lambda h and partial lambda h both vanish. Therefore, W and C both vanish. The free energy differences are also zero, and both fluctuation relations become trivial. In this case, the kernel may still reverse the protocol mathematically, but it cannot generate work or counterwork unless the Hamiltonian actually couples to the controlled parameter. Slide 15. Counteroperation under incomplete information. The counteroperation is asymmetric with respect to the original operation. The original operator fixes the final value of the control parameter. The counteroperator receives that endpoint and constructs an effective protocol that returns to the initial value. However, the counteroperator need not know the sign of delta Fw. Therefore, the counteroperation may be work extracting or work consuming, depending on the free energy landscape. The robust strategy is not to prescribe the sign of the counterwork. It is to enforce endpoint reversal while minimizing dissipated counterwork. Slide 16. Full cycle energetics. The present work focuses on the work-like driven stages, W and C. A complete energetic description of the full operation should also include the heat exchange during equilibration stages, internal energy changes, and total entropy production. This is important because the relaxation step between W and C contributes no work but can contribute heat. A future direction is therefore to describe the full cycle using the first law for each driven and relaxation stage. Slide 17. Takeaway. Let me close with the three main equations. First, the counterwork free energy difference is the negative of the original free energy difference. Second, the exponential average of the counterwork is the reciprocal of the exponential average of the original work. Third, the sum of the average work and average counterwork is non-negative. The main conceptual point is that counterwork is not minus W trajectory by trajectory. It is the ordinary work generated by an effective reversed protocol. The reversal is implemented by an active sign-inverting protocol memory kernel, and the thermodynamic bound remains intact.